So 9.1 is basically your review of SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent's opposite over adjacent. From that, you also get the reciprocal relationships, where you've got, for example, the cosecant is, that would be the hypotenuse over the opposite. For the secant, you're getting the secant is going to be the hypotenuse over the adjacent, and for the cotangent, you're getting the adjacent over opposite. And we've looked at that for the last couple of weeks. You've seen it before. We're going to be working here in 9.1 in the world of right triangles, where we're looking at the sines and cosines and secants and cosecants and cotangents, etc., in regard just to right angles. So this is simpler than what we just did when we were looking at general definitions for our sine, cosine, tangent, cosecant, secant, cotangent functions. However, some of the problems are pretty interesting. So let's look at a couple of examples. First, for some of the problems, just a little bit of vocabulary, and this came up in geometry class perhaps. If you're, say, on a mountain somewhere and you're looking down on some object from up here, they're going to talk about either the angle of inclination or the angle of depression, and that angle is always drawn to the horizontal. So that's going to be my angle of depression for angle of sight looking down on this object down here. Now at the same time, from that object in the bottom, if I'm looking up at something, I'm going to have what's called an angle of elevation. My angle of elevation is also drawn to the nearest horizontal, and you'll note if I've got a horizontal here and a horizontal here, those are parallel. That's a transversal, so alternate interiors, angle of depression and angle of elevation are going to be congruent. So first example, let's take a look at number 22 on page 336. Question states, a rectangle is 14 centimeters wide and 48 centimeters long. So not quite drawn to scale, but pretty reasonable, 14 by 48. And it says, find the measure of the acute angle between the diagonals. Well, a couple things to remember. Number one, the diagonals of a rectangle are congruent, so we should keep that in mind. The acute angle between the diagonals would be this one, or its vertical angle counterpart on the other side. How are we going to find the measure of that angle? Well, there's no right triangles in here right now, but I can create one by drawing an altitude right here. If I do that, I'm going to break up into 7 and 7, and this altitude where the midpoints of the diagonals meet is going to be halfway, so then I know that this is 24. If I go over that after that angle alpha, I know that the tangent of alpha equals 7 opposite over adjacent 24. So I could use tan inverse of 7/24 to get that angle alpha. And note that when I drop that diagonal in, or that altitude in, to this triangle right here, this triangle is going to be an isosceles triangle. If I drop that altitude in, it's going to bisect this angle. So if I can find alpha right here, if I just double alpha, I'll get the acute angle between the diagonals. So, situation here is we have a boat out here at position 1. There's an angle of elevation up to the top of a hill. Remember, we measure our angle of elevation in the nearest horizontal. Ship moves forward at a certain speed for a certain amount of time. It then is going to be closer, so its angle of elevation is going to be higher. Angle of elevation turns to 1.4. And from that information, knowing how far the boat traveled from point 1 to point 2, we're asked to determine the height of the mountain. So let's see how we can do that. If we draw each triangle separately from position 1, I'm going to look something like this. Let's call that height of the mountain here H. And I know that this angle right here is 1.1 degrees. Now I don't know how long this distance is. I do know, let's call the distance from P2 to the mountain. Let's call that X. Now we know that we go at, we're told that the speed is 4.5 knots for 20 minutes, so that's a third of an hour. And a knot is 60-80 feet per hour. So 4.5 times times 1/3, which will be our third of an hour. That's 1.5, and then I have to multiply that 1.5 times 60-80, and I get 9120 feet. So I know that that distance from P1 to P2 is 9120 feet. So therefore, on my big picture, that bottom base is going to be 9120 plus X. Now I also can draw the second triangle here from my second position. This is again from P1. From P2 here, my angle of elevation up is 1.4 degrees. Here's my H, and I know this distance is X. So if I look at the situation, I've got two equations and two unknowns that I've got to come up with. I've got an H and I got an X, and ideally I want to find H. Now it might be easier for me to find X first, and then once I found X, use a relationship to find H. But let's see how we can do this. Okay, so we have then our two triangles, and clearly we've got an acute angle, we've got relative to that acute angle, we've got an opposite side and adjacent side, so tangent seems to be pretty good way to relate things here. So I've got the tangent of 1.1 degrees equals H over 9120 plus X, and over here I've got the tangent of 1.4 degrees equals H over X. So two equations, two unknowns. How can I solve this? One strategy might be to set each expression equal to H, and then set those two expressions equal and solve for X. That's not a bad idea. If I do that, I get tangent of 1.1 times 9120 plus X equals H. And over here I get tangent of 1.4 degrees times X equals H. And then again, if two expressions are both equal to H, I can set them equal. So then I'm looking at tangent of 1.1 degrees times 9120 plus tangent of 1.1 degrees times X equals tangent of 1.4 degrees times X. And I'm looking here to solve for X. Well, if I can get the tangent X expressions on one side, factor out an X, then it looks like I'd be in pretty good shape to do this. So let's see what happens. I've got tangent, let's get my pen back. I got the tangent of 1.1 degrees times 9120 equals tangent of 1.4 degrees times X minus tangent of 1.1 degrees times X. Factor an X out, I then am going to get the tangent of 1.1 degrees times 9120 all over tangent of 1.4 minus tangent of 1.1 degrees equals X. At that point I got to grab my calculator and get X and get an approximation. And let's see what X is approximately equal to. So when I do that, I get x is about 33.428. Now go back in, I want to find what h is. Probably the easiest place to find h is going to be right there. So then I've got the tangent of 1.4 degrees equals h over, actually, I'm solving for h down below in one step, so let's do that. I've got tangent of 1.4 degrees times x, which is 33,428. That's about equal to h, and therefore I get h is about equal to, grabbing the calculator, is about equal to 817 feet. So again, quite a lot of work that went into that problem. A nice application of two equation and two unknowns with trig. Note that we had to draw some pictures. We had to be careful. There was a lot of work. There was a lot of work from step A to step T to get our final answer, and you needed to be organized.